with. So this is our new website, as you can see, all of you. MateriAlZ.org, and here we have a short message just trying to introduce you to this website. And on this section, which is the second section of the website, we are going to be posting the latest flyers every week. So this is going to be updated every week. And as you can see, Todd's with his brilliant smile is right there. And then we also have a small section about the organizers. And this is the thing which is particularly interesting, because we are going to be updating this in the spring. But for now, we just have the fall schedule. We actually have all the speakers also scheduled for the spring. So we are looking for a very exciting set of seminars, and you can actually find more about. So these lists will be actually populated and also updated with the titles as we get in touch with these people with their flyers coming back to us. Here's on this section. This is currently empty, but we plan on uploading the seminar recordings. It's actually linked to our YouTube channel. And then you can follow the YouTube channel here, and you can also get in touch with any of the committee members through this section. Actually, in the engineering mechanics and material science and engineering professor at the Penn State University. He has had prior experience of working at the Lawrence Livermore National Lab and the Applied Physics Lab at Penn State, and he is one of the leaders when it comes to additive manufacturing. And he has been instrumental in developing key solutions to a lot of additive manufacturing processes, and I'm sure is going to go over some of that today. And he has also been recently elected to the Welding Society. So I congratulate Todd for his excellent career, and we are looking for his seminar. Looking forward to his seminar. Thank you.
All right, so you're ready for me now?
Yes.
Okay, so thanks for the introduction. As I said, my name is Todd Palmer, and I'm a professor at Penn State. I've had been in the field now for a little over 20 years. I feel a little bit sort of honored to follow Marius Stan. I don't have any good Breaking Bad stories to provide or anything like that, but I will try to follow him up a little bit with a little different topic. So I think last week you probably learned a lot more about machine learning and computational material science. Today I'm going to sort of take a step back into what could be considered a little more of that fundamental metallurgy type of thing. And we're going to talk really about an area that I've been growing much more interested in, because I think it's an area that is a little bit untapped, but that I think has a lot of really good fundamental science and material science and metallurgy involved in it. And that is really in the area of metal powder feedstocks, or the metal powders that we actually use. As was mentioned, I started my career at Lawrence Livermore. I really cut my teeth as a welding and joining engineer. And so there I cut my teeth doing electron beam welding, laser welding within Lawrence Livermore, primarily for a lot of the other programmatic activities they had at Lawrence Livermore, not so much on the science side in that respect. I was also fortunate, one of my mentors at Lawrence Livermore was John Elmer. And so if you run into John, you know of all the great things he's done in the welding and joining field. But also, I think primarily one of the things that I was really fortunate as a student to be able to do was work with John on his really seminal work in the use of in situ X-ray diffraction to understand phase transformations in welding and joining processes. And so if you really want to get to metallurgy and material sciences at its core, it really happens sort of on a beam line when you're heating or welding a sample up. And I must say, when we started these experiments at Stanford, we were a little bit of a novelty to the physicists on the beam lines, because they couldn't believe there were these two welding engineers with a welding torch welding titanium in a hutch and using the X-rays off the synchrotron to really start to try to understand what was going on in a lot of these types of structures. But outside of that, so a lot of that really is going to paint the way I approach what's going on with the feedstocks and the properties. And we're going to see a little bit of work we've been doing on not only characterizing feedstocks, but also in looking at how those chemistries and compositions of the feedstocks really start to impact the follow-on properties of additively manufactured materials. So before I go too much further, I do want to start with my acknowledgements. I listed a lot of my students, but also sort of at Penn State, a little bit sort of contractually obligated to talk about the, and this is the only time I'm going to say the title, because the title's a little long, is the Center for Innovative Materials Processing through Direct Digital Deposition. Sort of have to take a breath after you finish that, unless you're like a professional singer. But what it is really the focus point for a lot of these systems that we have at Penn State. And we have a wide range of both powder bed systems, hopefully you can see my cursor here, of a number of 3D systems, because we do have a bit of a relationship with 3D systems. They have an engineer on site that really is running sort of the ProX 320, the ProX 200, which was the original Phoenix systems, have an EOS M280, some of the directed energy systems. So if you go back, a lot of times people will tell you there's nothing new under the sun, and they are correct about that. Is really, I sort of count, I really think we're sort of in late second, third generation of additive manufacturing. So we hear how it's new and it's how it's going to change everything, but that's not really the case. I heard these same arguments in the 1990s when the directed energy processes, whether it was Optimec or the lens process being developed at Sandia, or the directed light fabrication techniques being developed at Los Alamos, where these types of layer by layer processes were there. As a welding and joining engineer, you know, the next words out of my mouth are going to be is this is nothing but welding when it really comes down to it. And it does tend to be that case. And we see that especially with sort of these directed energy systems, sort of like an Optimec lens. And then there's a hybrid system here at Penn State as well. Another couple other characterization systems, one in particular that is really helpful in a lot of the things we do, and in some cases maybe it's a little overused, is X-ray CT scanning or computed tomography. So it gives us sort of a CAT scan of metals. Gives us a nice way to find porosity, but you need to be careful about sometimes what it actually tells you. So a number of the students I've had, professors I've worked with, students come and gone at different places and some of the different departments and sort of the funding agencies that have funded portions of the work that are presented here. There's other work that has been funded. So with that, I sort of want to start initially with how do we characterize feedstocks? So you end up with a metal powder. You buy a metal powder from one of the remaining powder manufacturers out there, or you buy it directly from a machine manufacturer. How do you specify that powder that's going to work on that system? Most of the time, unfortunately, I think a way to look at it is we're just taking somebody's word for it. Is a manufacturer tells us this powder should work, and we basically agree with them. We say, okay, fine. As a scientist and engineer, probably not a real good attitude to take. You really should be, and I'll direct this more at the students, is skeptical when people tell you if it's too good to be true, it probably is. And so we'll get a little bit into some of these characterizations, and another area that I'm really starting to think a little more about is in the area of rheology. And what this is really starting to understand and use some tools that are used for polymers. I mean, when I first started thinking of powders and I ran into people talking about rheology, I had to go look it up. I didn't know really what it was. As a metallurgist, you don't really deal that much with rheology. That's something the polymer scientist people do. But if we think about metal powders, we're going to find that they do behave a lot like liquids when they're considered in a mass. And so a lot of the things that the polymers people and the rheologists had looked at is going to become really important as we start moving forward in additive manufacturing. And I'm going to come back to the point, is in additive manufacturing, we have a manufacturing component directly in what we're talking about. So there has to be some level of application here. And so as students and young scientists and engineers, you need to think about, how am I going to specify it? How am I going to make 10,000 widgets, 100,000 widgets? How are they going to be the same all the time? How am I going to expect that things are going to work as they're expected to. So being able to understand these characterization tools and understanding actually what they tell you and how they work and how they can be impacted by different changes in powder properties is a really key area. Another one is how you make the powder. So we'll go over that a little bit, and mostly we're going to see is gas atomization is the primary method. I'm going to focus on gas atomization for now, but there are a number of different processes that are arising out there that we really should be paying attention to. One is called a plasma atomization process, which is very similar to some of the plasma spheritization processes that are out there. We can also water atomize powder, but we need to be a little careful with how we go about specifying that powder and using that powder. And then I'm going to talk a little bit about composition variations. And when I talk about composition variations, I'm talking about something that will meet a current specification for the material. So if you go into the ASTM standards for a nickel chrome moly alloy, this alloy will fall within those specifications. But what we're going to see is if we take one or two alloying elements and move them from minimum to maximum areas, and most alloys, most specifications were written by people who make the materials. At first glance, we will say to ourselves, well, of course, those are the people who know how to do it. The opposite side of that coin is that they're going to try to make the specifications and the standards as wide as possible so they can sell you product more easily and more inexpensively. So the minute specifications get tightened up, the cost of the product goes up. So, or at least to make it, they can still sell it to you at a premium. But these compositional variations are going to impact that. And I want to finish it up a little bit with everybody had a roadmap over the last few years, and we weren't immune from that. We had to jump on the bandwagon. And so I'm going to do a little bit of selfish promotion and promote some stuff that we talked about primarily with materials. Now, moving on from there, I like to start with this slide for no other reason than I like to highlight one word, is even ASTM was able to see that this is really a welding process that we're talking about. So the fourth word, pretty important up there, and I made sure I made it big so everybody could see it and couldn't deny that it's there, is a process of joining materials. This could be something that the American Welding Society had put out there as far as a definition for additive manufacturing. And so, you know, a lot of people focus on the 3D modeling data, this layer by layer, other types of processing routes. But I like to focus on the joining, because when you start joining materials, especially through fusion-based processes, you really start to develop some metallurgy and some interactions and things that are not what you would expect to see out of a binary phase diagram or more conventional Wrought processing routes. And so it's important to sort of keep that in mind. So when we start talking about welding and different things like that, we're going to see that that sort of falls in there. Now, there's a whole range of different things. I'd be remiss if I didn't show the robotic hand from our friends at the manufacturing demonstration facility at Oak Ridge, or some of the other parts, or even upwards of things we've done at Penn State. This was one of my most motivated undergraduate students. That was a front upright for a Formula SAE car that was designed and fabricated out of titanium. This student was also a great salesman, I would say, is he convinced EOS to fabricate this part for him for no cost. So he was very, very good student. It was very much a design exercise, but it came out being a very intricate type part. And into these large bulky components. Now this is an electron beam, or what a lot of people will call a SIACI type system, mostly because SIACI builds the electron beam systems. It's an electron beam welder with a wire feeder, or in this case, 2 wire feeders. And what they're building here, in all likelihood, I can't say for certain, but they've been sort of showing this off, is tantalum. So they're feeding wire as their feedstock rather than powder, which was originating from here. Now, going from powder bed fusion to directed energy deposition, we have some differences. And I'm going to get away a little bit from sort of showing off the processes where, you know, most everybody would go in this type of presentation. and talk a little more about what goes into the powder. Now, when we start talking about powder, we have to sort of think in terms of particle size distribution, or the particle size range. Now, these are measured through laser scattering techniques. You can use image analysis techniques, and we're going to see that there's a couple different ways to sort of talk about what goes into the powders. But powder bed fusion powders in general are going to be spherical. They're primarily gas atomized. You'll see in the literature every once in a while where some people will use some really spherical water atomizers. Some people who really knew how to water atomize powder provided them powder. Packing of the powder tends to be a little more important, because when we start looking at the physics involved here with the process, the laser absorptivity is really going to be impacted by the packing as the laser enters that powder bed. Is how that powder lays down, how it packs, how it sort of sits together is going to make a big difference. Now, powder size distributions from versus a directed energy where we're flowing powder through nozzles and into a weld pool. The powder sizes in powder bed fusion tend to be smaller. So we're looking at a finer powder size, 20, 30, 40, usually at 30 to 40 microns, where most people will feel comfortable. We'll see a little higher size distribution if we switch from a laser powder bed fusion to an electron beam powder bed fusion. If we switch over to binder jet, we're going to see something even finer still. So those can vary down into the sub 10 micron level, where I will warn you, when it comes to sort of safety, you got some real safety issues when your powders get really fine, because most of the metal powders we're talking about, if you go to certain national labs, they will tell you that there are different things like that. So there needs to be some care taken, and there need to be some real safety issues when it comes to looking at powder bed fusion and some of these powders. And even in directed energy, even though they're larger, powder size. So the powder size in most directed energy deposition processes will tend to fall in a 50 to 150 micron, usually about halfway through there, about 100 microns. The idea here is that they're spherical, but they need to be able to flow through these nozzles. Now, this is where sort of I start with my Festivus-like listing of grievances as far as powders available. And so when we start talking about what powders are used in additive manufacturing for metallic type systems, what we really start looking at is basic alloy systems, sort of these generalized ones of aluminum, cobalt, nickel, steel, titanium. And if I were to look at these alloys, and putting my curmudgeon hat on, which I really don't have to most of the time, because it's sort of the way I tend to think, is every one of these alloys was developed for something else. Ti-6-4, I think it's the second of the titanium alloys to come out. Cast wrought system. H13 tool steel started out as basically a powder system for powder metallurgy. 316L, cast wrought. 17-4, cast wrought. Starting to get the key here. Every one of these alloys was designed to be processed in a certain way. And as a materials scientist, materials engineer, whatever you want to consider yourself, when people really start talking about materials, there are three words that should come to mind: is process, structure, and properties. Those really govern the way we should be approaching materials and how we think about them. All of these materials were designed, and design of alloys and materials should involve how they're going to be processed up front. That's our boundary conditions for it. And what are we doing? We're taking a material that was designed to be processed in a very specific way with a series of complex thermomechanical heat treatments. We're going to convert them into powder, melt them with a laser, and then we're going to expect them to operate in the same way or have the same properties as something that took years of analysis and study to perform. It's one of our real weaknesses is we really don't think about how these alloy systems are being impacted by this change in processing routes. And then we make things even worse. You know, we start off, and when we start thinking of additive manufacturing processes, we're gonna really start thinking of, hey, we can make some really nice trinkets. We can make some cool designs. We can make lattice structures. We can do all this. We can take topological optimization and cut weight and do all these things. But when it comes down to, there's sort of a point where you need to think about the complexities and what you're actually doing to the materials. Because the materials were never meant to be treated in this way. I would typically joke that the designers of Ti 6.4 are rolling in their graves at what we're doing to the alloy system that they developed and the things we're expecting out of them. And I like this plot mostly because it sort of shows all the really complex things we're doing. Not only sort of starting from a computational materials standpoint of different things, and I'm not going to talk about it too much here, but you know, really thinking of equilibrium partitioning and solidification, thinking of how a Scheil type simulation is actually a better way to predict the microstructures that we're seeing further down. We're taking powder feedstocks, and we're going to go into a few points here of how complex most powder feedstocks are. Beam material interactions. We're taking a bunch of powder and melting it with a laser. I can remember my physical metallurgy professor back as an undergraduate. First thing he said was when he introduced sort of the welding modules, he said the best way to ruin a perfectly good piece of metal was to weld it. And what are we doing? We're taking these materials and we're welding them tens of thousands to hundreds of thousands of times. So we're probably not doing very good things to them. The melt pool dynamics as well. So my PhD advisor here at Penn State was Professor DeBroy. And so I came out of a group that did heat transfer and fluid flow modeling. We did Navier-Stokes type modeling of weld pools. And so in addition to all of these other things of interacting a beam with the materials, we're producing large amounts of fluid flow and very large temperature gradients. They're going to lead to defects, whether they're gas pores, whether it's from keyhole collapse, where we are making keyholes, no matter what anybody may want to say. Lack of fusion defects. So how do we get rid of these defects? Now we want to hot isostatically press these materials, and then we're going to end up with a certain amount of properties. So you add all that together. I put it in a circle just to sort of show how these properties and then the chemistry and everything that we have in these areas. There's a lot going on. And for our ability to really predict what's going to happen in additive manufacturing is going to depend, and I want to start thinking of the powder feedstocks. And so going beyond that and thinking in terms of the powder feedstocks, we have a lot of things going on here. And if any of you have run into Sean Kelly when he was at Orlicon or EWI, or I think now he's at SLM, we used to sit and talk about these things. And one thing that he liked to usually tell people was, you know, the interesting thing about additive manufacturing is that you're making the material at the same time you're fabricating the part. Now, if we think of how components and complex components are made, usually my comment to my students in my introductory materials classes is if you can't weld it, you can't build it, or you can't make it. And so we usually start with some type of material, and it comes in a structural form. Steel companies, nickel companies, titanium companies, this is how they make their money. They sell you a plate, a bar, a rod, some other type of product form. Now it's your job to make that into something. You're either going to machine it into something, you're going to cut things away, you're going to bend it, you're going to form it, you're going to roll it, you're going to weld it at some point in time. In additive manufacturing, we're sort of taking that all out. So the idea of geometries and features and how they affect process structure property relationships becomes really important. So there's a design component. As a materials engineer, as I said, I've been working for over 20 years now in the field. And it was always amazing, especially as a welder. And this goes back to my days at Lawrence Livermore, working DoD programs at the Applied Research Lab at Penn State. The last people in the room were always the welders. So decisions were made on design and everything else. And the only time I was called as a welding engineer was when something broke. Now, in the additive manufacturing area, you sort of need to talk to the materials people up front. They need to be there because their materials properties are going to be impacted right from the get-go of your design of your part, and these material and these property, structure property relationships are going to be impacted. So cracking is going to occur, porosity formation, gas absorption. All of these things are getting into the processing, they're affecting the material properties. And I think for really the first time, and this is something that makes additive manufacturing a couple things, makes it really interesting from a research perspective and risk analysis standpoint. This is frightening to no end, because really what has happened is that all the risk now is on the people who make the parts. You used to be able to divvy up that risk among different people. If the materials weren't right, you went and blamed the steel company or the nickel-based company. Now you have nobody but yourself to blame when something goes wrong. So the risk is definitely assumed, but product performance and reliability, it all comes down to, and because I'm talking about powders, it's going to come down to what you do with those powders. So how are you going to specify the powders? First off, how are powders made? Not something we really run into a lot. Here in Pennsylvania, and I see one of my students on the list here of attendees. We're a little fortunate here in Pennsylvania when it comes to sort of the additive manufacturing field and the powder field, because we actually have probably about everything we would need as far as people who make powders, probably within about a 3 to 4 hour drive of us. There aren't a whole lot of powder companies out there who we can't really come and deal with. And so if I drive about 6 hours, I go to Glen Falls, I can find somebody who designs atomizers. And so I tend to think of 3 ways of atomization. So there's some other different ways to make powders. You can mill them, you can do a lot of things, but they don't really give you these spherical powders that we seem to really be demanding for additive processes. The primary method is going to be gas atomization, where you take a melt, you run it through a nozzle, you hit the nozzle with high impact gas, and it creates particles. Plasma atomization is usually starting from a wire feedstock or some other type of feedstock. You can use plasma torches. What you'll see here is, I think the company's name now is 6K Technologies. They tend to use this type of process. Instead of plasma torches, in some cases, they'll use microwave generators to produce powder feedstock. And one of my favorites is centrifugal atomization, where you take a rod, you spin it at about 3,000 RPM, you take a torch on the end of it, and you melt the tip of the bar, and it, as it's spinning that fast, it centrifugally throws off powder beads. Now, we notice these are all getting spherical, and it has to do with sort of the size of the atomization chamber and basically having enough superheat that as the powders fly off, they're still molten, and then nature wants them to become spherical because it's trying to reduce its surface energy. So that's why you end up with spherical particles at the end of the day. Now, in most of these atomization systems, especially in gas atomization systems, the cost is not down here. It's not in the actual chamber where you're doing the atomization. The cost is not really even in the nozzles, even though the nozzles, and I don't know if Ivor Anderson is here, but at Ames, he's the leader now on the design of nozzles and gas atomization. Your cost is up here, because if you're talking about nickel and titanium-based alloys, you're looking at vacuum induction melting. Anytime I add the word vacuum into front of anything that's going to be processing large amounts of metal, you can start adding, you get your checkbook out and you start adding a lot of zeros onto the end. And I'm not talking on the cents side. So your cost is really going in here and creating the environment. Now, with all this surface area on these powders, no matter how much you control the environment in here, they're going to pick up other things like oxygen, like hydrogen. There's a lot of people who really get caught up with charge on powders. They pick up electrostatic charge. They're really good at picking up moisture too. As you know that if you drop a small drop of water on some flour and see what happens there. So metal powders can be made, and these are the three primary ways we're going to talk about here. There's a lot of other ways to do it, but for additive manufacturing, these are the ones. Now, normally, and the zoom here is sort of taken out, and I give sort of these lectures, I would probably go harass somebody, is how spherical does this powder look? That doesn't look too spherical. Looks like there's a lot of satellites, some smaller particles. That one's not very spherical either. So we start looking at these powders, I mean, how close are we really to sort of saying that they're spherical? Now, the plasma atomization and the centrifugal atomization, those can be pretty spherical. What I'll tell you about centrifugal atomization, though, is that it's extremely expensive. These powder particles may look great, but they're limited in size distribution. So they really only fall in the size distribution that they're really useful for directed energy processes. And if you want to talk about the cost of running these systems, there's basically one company in the US that does traditional centrifugal or prep type powder, and they had to be bought out and saved by the government. It is not a very economical way to make powder, and it tends to be limited to titanium and Inconel 718. Gas atomization is where you're going to mostly see things. Now, when you buy something, so you got, say, I don't want to really say too many people, but I'll say Sandvik, Osprey, and Carpenter Technologies, or Carpenter powder products. You want to buy gas atomized powder, those are the ones to, two of the people you go to. There are other people out there. I don't want to sort of name anybody without sort of naming others. But when you get there is, how do you specify that powder? So you're going to buy some powder, and you want to sort of know is, okay, particle size is definitely a start, and then all of these other things. So powders, because you have all that surface and all these powder particles, is you have all kinds of different things happening. So composition is one that maybe you can control. Homogeneity, how similar are the particles. Contamination is another one, but sort of this internal structure is a tough one, and we're going to show you how to measure that. Not an easy thing to measure. Flow and packing, now we're starting to talk about things that we could potentially use. So how are they measured? Now, the first place we usually go is right back to the traditional powder metallurgy industry. These are people who press parts, sinter them in furnaces, sell them primarily to the automotive industry. So basically iron powder metallurgy. Very simple tests. Hall flow meter. Put 50 grams of powder into a funnel with like a 6mm orifice. Have a stopwatch. Put your finger over the orifice. Start the stopwatch, pull your finger away, measure how long it takes for the powder to fill a cup. You can measure the apparent density in that cup, basically, of how much that 50, how much it gives you in to fill that cup. Tap density, very similar to filling the sugar container. You run out of room in the sugar container, you shake it up a little bit, you get more packing. You can measure that tap density, angular repose, particle size measurements, and even image analysis. These are ways to characterize them. They're very simple tests, but they were really designed to measure a powder being able to fill a mold with the same amount of powder in the same amount of time each and every time. Doesn't really reflect what we see in powder-based additive manufacturing, where we're taking a blade and basically skimming and making a powder layer or flowing powder through nozzles. So this particle size distribution is the first place we start. It's a fairly common test, pretty simple. We can use laser diffraction techniques where we disperse a powder in there and basically look at small angle and large angle scattering. We get an idea of what the distribution of particle sizes are. Or we can take the brute force approach. And with computers these days and basically image analysis tools, we can go through and do a brute force and measure each and every particle that we see. We can measure hundreds of thousands of particles in this way. It's a very good measure. So these are some actual images, backlit images of powder particles. So how spherical are all of they? Not as much as we would hope. So that lets us go with that is to start to think of particle morphology. Convexity is one, and this is basically variations on the particle surface. Aspect ratio tells us how close it is really to a circle, and circularity is how close that 2D projection can fit a perfect circle. So you start looking at some of these, you can get some wide variations in particle morphology. Now, particle size and morphology are only a couple things. So that gives us that particle size distribution, gives us that morphology. But there's a lot more that goes into sort of these bulk powder behaviors that we're talking about. We know flow rate, angle of repose, all of these general things, but there's things within the powders that are going there. And that's where some of these newer tools are coming in. Now, I like to show this just as one way. Now, I see a lot of these kinds of simulations out there. And one of the things that I don't see is really an accurate representation in these images of the powders themselves. What you'll notice on here is the colors are basically there to just sort of let you be able to tell the difference between different particles. But what's really missing here, and we're just, in this case, just getting an idea of trying to simulate an angle of repose, and we can get pretty close. But the things we don't always worry about, and we tend to see it here, is we change particle sizes. The other thing is each and every one of these is based on spherical particles. And I was making a big point of it before, and I'm sure a lot of you caught on that, was that, hey, not all these particles are spherical. Some of them are far from spherical. Some of them even have some internal porosity in them that's going to change it. So each one of these simulations are really nice to look at. My concern really becomes, how can we use them? And so this is sort of where we need to think about the powders. And so in this case, this is getting a little more into one of the studies that we've been doing, and we're really getting ready to try to publish a lot of this material, is what happens if I change the gas that I atomize with? And it's a common consideration, primarily up front of a way to sort of adjust my composition. I may change atomization gases as well from a cost perspective. Nitrogen is a whole lot cheaper than argon. If you've bought argon recently, you start to see, and I bought a lot of argon to build a lot of the components that we built. And I will tell you that it gets costly pretty quickly. Now, just looking at these powders, the chemical compositions, the chemistry, so I have two different lots. I chose two different manufacturers that gave me two different nitrogen atomized 316Ls. And I actually found one producer who I think they were playing around, and I got lucky. They just happened to have some argon atomized 316L. And so they used argon as the atomization gas. And so I said, hey, send me that. We want to take a look at what happens. Initially, from a chemistry standpoint, but when we started looking at the powders, we started saying, like, you really look closely at these, they are different. There's some difference there. But it's not anything I can really quantify or I can really understand. They just sort of look smoother. Now, what does that mean? So we looked at the nitrogen concentrations, and if you've done any welding of 316 or really thought about austenitic stainless steels, you start looking at these and you're like, yep, chrome looks good, nickel, manganese looks good, silicon, molybdenum is there, definitely L's with the low carbons, sulfur's decent. Oh, we see a big difference in the nitrogen levels. And really, as a welder and sort of coming out with stainless steels, that's usually a big red flag, that something is going to be different. Nitrogen is really a well-known austenite stabilizer. We're going to see when I start talking about the pH grade stainlesses that this is a big deal with that. And even here we see, these are just some engineering stress strain curves. Low nitrogen levels, that's a pretty significant, that's over 100 megapascals really in yield strength coming out there. And probably right around the same, maybe a little less in ultimate tensils. There's some real differences in just how we atomize the powder, but if I were to just buy these powders just as an idea of meeting the specs, I would tend to assume that they were all the same. Obvious that they're not. You notice I also added a couple other columns down here with identifying chrome equivalents, nickel equivalents. What these are sort of welder shortcuts. So they come out of the idea, initially it was called a Scheffler diagram. DeLong came around in the 70s, added nitrogen to the Scheffler diagram. And then there's a WRC 1992 diagram. So if there's anybody from, and I'll say it as a Penn Stater, is that school in Columbus, some people there and people at Lincoln Electric had worked on that and understood that. So what it gives you is an idea of the other alloying elements that might contribute. Chrome is a ferrite stabilizer, nickel is an austenite stabilizer. And so how these different alloying compositions can impact that. And what we tend to see here is really the impact of the nitrogen, the increased nitrogen levels versus what we see in the argon atomized. Now, if we look at these three powder lots, you know, if we're looking at it from a particle size distribution, we're not seeing any real difference. We're seeing basically similar volume percents, similar sort of number percents, a couple different ways. So volume percent is for each of these diameters, the volume of the powder that's measured, the number or the number density. This, usually looking at things on a number density distribution, will sort of amplify the presence of fines, and we see some of that here. Now, when we start looking at morphologies, what we do is we look at it as a cumulative distribution. And one of the things that really came out here is this change in aspect ratio, where we have basically the argon atomized is showing us a much higher circular shape. So its aspect ratio is much closer. A portion of the particles, their aspect ratios by about 10% here are more spherical. So we're starting to identify some differences between an argon and a nitrogen atomized powder. We don't really see too many differences here. You know, they were conducted, you know, everything was pretty much the same. It's not anything that we would really run out and say, there's what our difference is. Everything was pretty much the same. Now, this led us into sort of trying to take a look at rheology tools, because we're seeing differences in spherical. We're sort of saying like, okay, do these powders really vary? And so when it comes to rheology, there are three that I want to sort of focus on. One is a rotating drum method, where for the most part, you take a drum of powder, you take a known volume, and you rotate it around. And so what you're doing is you see how the powder is acting like a liquid. It climbs up the side and then it collapses down. That gives you an idea of what we consider the avalanche angle or the avalanche energy. And so by measuring that angle, it gives us an idea of the flowability. Another way is to take a blade and run it through a column filled with the powder. A shear cell is another way to do it, and this is primarily a way to measure permeability. And what is happening here, for the most part, is the shear cell is going down, there's a certain pressure, and then it's measuring the forces and torques as it turns. Or you're running gas flow up through it, and it's trying to measure the amount of gas flowing through. So these were the two systems that we looked at, and it gives us this ability to look at how these powders are going to behave as a fluid. And so, you know, flowability is one. And, you know, sort of with me, I'm trying to sort of take a step back from it, because terms like flowability, spreadability are really misused. A lot of people are out there making claims that I can measure spreadability, I can measure flowability, but it's not really that well defined. And in these different tests measure flowability in different ways, and they use different characteristics or measurements that they're making to find them. In the rotating drum, what we typically are seeing is avalanche angle. It's a geometry type thing. And what we tended to find here is that this geometry, this simple test, basically rotating a drum and measuring this avalanche angle, was actually pretty good at finding a difference between the powders. Really, the argon powder with a lower avalanche angle shows better flow characteristics than the two nitrogen powders. Now, we definitely see that when we apply that as a cumulative distribution. And so higher resistance, lower flowability. This is a pretty significant difference in flowability. So the argon atomized powders, using the rheology, now we can start sort of discerning some of these differences in the powders. Now, when we look at sort of a more traditional powder rheometer and a blade, we didn't really see these same differences, surprisingly. We didn't really get the same type of ideas. What we found was that there was no real trend to them. They sort of were sort of in the middle, or they displayed really different type trends. All of a sudden, you know, one of the nitrogen atomized has this type of process. Now, we saw these different results, now we started asking ourselves, what's going on in this? I'll jump back, and don't worry, I do this to my students all the time. So how is this measurement being made? So I'm looking at a blade and I'm pushing powder with this blade. So one of the things that's going to go into this type of measurement is the mass of that powder in front of the blade. So a couple of my students started looking at some other powders, and what this is a cross section. And so if you really start looking at powders, what you're going to start seeing is like they are not as dense as we would hope. A lot of them have porosity in them. And so that porosity, even though it has a certain volume, it means its mass is actually lower. So the density and these numbers that have gone into some of these calculations, and really these systems are measuring very few things. They're doing a lot of calculations based off a limited number of measurements in order to come up with these different parameters. So we wanted to try to get an idea of how accurate or how much porosity is in powders, because you hear people talk a lot about, well, there's porosity in powders. There are some people claiming that the porosity is carried over to porosity in powder bed fusion or additive manufacture type things. And we're not going to talk about that right now. But we took some powders, we filled some 3mm by 3mm tubes, and we CT scanned them. Now, CT scanning is really cool. It's a way to look at differences in those. But if we start pulling individual scans out of there, we start seeing that there's a lot more porosity in these powders than we ever really would have thought. And one of the things that you'll hear a lot is that there's this tendency for there to be these much higher levels of porosity in an argon atomized powder versus a nitrogen atomized powder. Part of it is that a lot of the original theories in atomization based on porosity in powder particles was based on gas absorption. So argon isn't going to be absorbed, so it must be forming more pores. There's some other bag breakup and some other methods to think about it, but what we tend to see here is that, you know, between about 3 and 5% of the particles by volume have porosity in them. That's 3 to 5% error in mass. You start thinking about that, that can be driving some of these differences that we had. And so we start looking at some of the different number fractions and sort of how they come with a cumulative distribution. We can start quantifying it. And so we can then start thinking in terms of other ways. So we have some pores, and so our mass isn't what we really thought it was going to be. The next thing is to think about is I have a whole lot of powder in here. And one of our issues initially, and this is a better one to sort of see it in, is that the void space is not just internal to the powders. It's also external to them, and it sits in how the particles pack. And so a way to measure that is through a permeability test, where you basically flow air through the powder with a normal stress on the surface. And what we tended to find on here was that there were differences in the permeability between the powders, and they were primarily one of the nitrogen atomized powders had a much higher permeability, which means it was really a difference. So they didn't follow the bulk packing density. So we went and figured out the void spacing. And void spacing in this case gave us some idea of how different powder particles mentioned. So by taking this, we tended to see is that permeability is more dependent on this void spacing rather than what we might consider as bulk packing density, partly because some of that bulk packing density is being impacted by that internal porosity. So we can start to see that powders are a lot more complex than what we would have initially thought. And being able to sort of characterize them and understand how they're interacting with each other is going to impact things down the line like laser absorptivity. So I have another paper, and I'm not going to talk about that here, that I worked on with some people from NIST in Boulder, Colorado, of basically trying to quantify the differences between spreading and packing of powders and laser absorptivity. And there's some definite relationships to keep in mind. Now, let's go back to this atomization gas. I'm going to switch gears here a little bit and go to a precipitation hardened stainless steel. Now, these are some really common ones that are out there. And what these steels require is post-processing. So going back to the powder feedstock and what gas we're choosing for that atomization gas, the processing gas, we hear a lot of people talk about processing gas, but we've found with, especially in powder bed fusion, that it's not quite as important or as big of a factor as this atomization gas. This is a way to introduce large amounts or really cut back on the amount of diatomic gases you may have in your feedstock. But on this is all of these impact post-processing. Now this is one thing, if I'm going to get up on my soapbox, there's a couple different ways in science of going about this. There's being the first one to report something, and then there's the issue of whether it is correct or incorrect. So there was a lot of literature out there, a lot of papers written initially on these alloys that over the course of time have been proven to be incorrect and have led us in the wrong direction. And my sole reason for going into some of this was to try to correct some of that in the literature. I never would have done this in-depth of an analysis without that. But what we tend to see here, and I wanted to concentrate on, is the differences in nitrogen. Now we see some difference in manganese and that, but nitrogen versus argon atomized. And we're going to stick primarily with these two over here. So we see almost an order of magnitude difference in nitrogen between an argon atomized and a nitrogen atomized pH grade powder. Now these mechanical responses are taken from the literature. If you're a designer, there is no way that you can start designing for pH grade stainless steels or 17 chrome 4 nickel. In this case, with such a wide disparity in the as deposited levels. And we found that these are based on retained austenite. pH grade stainlesses should have primarily a martensitic microstructure. We're going to find that if you add a lot of nitrogen to it, you start retaining large amounts of austenite. So you've got martensite and austenite. The austenite is going to transform with strain. So you end up with these trip type effects. Now, if we start thinking of the composition, so we can go back and think about it. So we have argon and nitrogen atomized. We're going to go back to a welder's tool, which is back to that nickel and chrome equivalent issue that I had talked about before. Now, just by changing the nitrogen amount, I have gone with these letters represent or solidification mode. So I would expect something to solidify as austenite or solidify as a martensite or ferrite. What I've seen here is I've changed my modes at which my microstructure should form. Both of these alloys meet specifications. So it becomes that issue of how we can do that. Now, if we look at computational thermodynamics and just pulling out thermocalc, just running some pretty straightforward calculations, we find that the argon atomized actually has a delta ferrite forming out of the liquid. You can see remnants of this in the alloys or in the as deposited materials. In the nitrogen atomized, it solidifies as austenite. So we have completely different microstructures that form. Copper phase is at a little lower temperature. What we start to see is our carbides and our nitrides are starting to impact here as well. The other thing to look at is there is thermodynamically a small amount of austenite that could be stable even down to low temperatures, whereas we see it basically disappears in the argon atomized materials. As deposited microstructures can change as well. And so these are some EBSD maps and phase maps showing something in the argon atomized. It's almost completely martensitic. In the nitrogen atomized, it's almost completely retained austenite. And so that's sort of where these differences come in. Now, a little trick here. The austenite here, this retained austenite, will transform to martensite when you polish it. So in order to obtain these nice, pretty pictures with our EBSD, we had to ion mill the surfaces. So we went through the polishing, went to a colloidal silica suspension, and then when we would try to look at the EBSD with that, we would find that everything was martensite. XRD had told us before that it was austenite. So we actually had to revise our sample preparation procedures in order to see this. And that is a little bit of that delta ferrite sort of in this microstructure. So we have evidence that it's there. Now, what these did that really sort of flummoxed us a little bit was the appearance of all this retained austenite when we tried to run these through traditional heat post-process aging treatment. So you have to solutionize and age the materials after they're done in order to obtain the properties you want. What we found was that the argon atomized behaved as expected. That's right on with you should get to a peak aging at about 495, and it should decrease as you move your way down. Nitrogen acted in the opposite way, which really got us thinking, okay, why is that? So it's telling us that we actually underaged when we thought we were peak aging in the nitrogen atomized. So we had to keep going up in temperature, and we found that we end up with a peak aging condition, and the hardness matches that peak aging condition somewhere around 620 to 650 degrees C. So the alloys, the literature was telling everybody that you couldn't age nitrogen atomized materials. We really came to say you need to age them properly is a better way to do that. Now, when we start looking at that, we started wanting to connect material properties, and I know I'm running a little long, so I'm going to sort of speed up a little bit, but start looking at it, wrought and aged in the argon, it tends to fall a little short of what we would expect with the age. But if we do digital image correlation of them, we tend to see fairly uniform strain fields. Now, let's go to the nitrogen atomized powders. That retained austenite is going to give us the fun stuff here, where we start looking at this interrupted yield point, and we start seeing the presence of Luder's bands there. And then as we go up, we see it again. So we see a couple places within the curve where we're actually starting to convert that retained austenite through strain-based processes into martensite. And what happens at peak aging? The nitrogen atomized, even under peak aging conditions, we have a little interrupted portion where this type of inflection point in our nitrogen atomized yield string, that is transformation of that retained austenite. So we can beat the standards, but this was one that I wanted to sort of talk about, and I make a big deal of this. SAE International came out with a recent standard, and what they did was they limited the amount of nitrogen. They basically precluded the use of nitrogen atomized powders, even though if we look at it, we can obtain significantly higher strengths. And there's work being done looking at corrosion resistance of some of these nitrogen atomized powders, and they are extremely attractive for a number of ways. So by understanding how to process these materials, and we get a little better idea at peak aging of how much stronger the nitrogen atomized are, how much more ductility they have. There are a lot of benefits to thinking of nitrogen atomized powders or high nitrogen levels versus argon atomized levels. So what I do want to talk a little bit about is some other types of compositional variations. And I'll try to keep this short because I know I'm really running over and probably running into your lunch times in Arizona, and I apologize for that. I get excited about this and you can't stop me. So you can ask my students who are here, they'll attest to that. But one thing that's been sort of bugging me for years was a common alloy, alloy 625. And when I looked at the standards, I was always like, wow, that seems to be something rather broad and curious. Why would you allow up to 5% with no minimum? You know, it's like, that's a lot of iron. It's got to be doing something. So I was constantly sort of told it's not a big deal. They let it flow. I never quite bought it. So when we started doing some of the additive manufacturing stuff, I had a small program and I was sort of saying, I went to one of the powder manufacturers and I convinced them to find me two heats, one with low iron and one with high iron. And we built some parts with it. And so, we did some differences in the powders. We always have to take pictures of the powders anyway. So a lot of satellites, some interesting stuff on the high iron content. Now we started looking at the literature, and when you look at it, this goes back to my old friend John DuPont at Lehigh, who did a lot of great work back in the 90s. So did Mike Cieslak and the guys at Sandia on really looking at solidification modes and starting to understand where law-based phase form and how when you start welding some of these alloys, some of the issues you run into, whether you have carbide formation or law-based phase formation. And so they did a lot of great work, and they sort of found various in arc welding and overlays, and 625 is widely used across maritime industry for weld overlays. Nuclear industry, it's constantly used in the same type of situation. And so they really came on, this is Mike Cieslak back in even the late 80s, of looking at, we need to control silicon, carbon, and niobium to limit this secondary phase, because there's this propensity to form these phases. And so they really were tying into the formation of law-based phase with the addition of iron. And that was typically done through overlays and really the dilution of the iron from the underlying substrate into the Inconel. And so high iron was really traditionally linked to this idea that I'm going to form a lot of law-based phase. Now, we sort of did the same type of thing. What we started to see in our microstructures, and these are some as deposited ones, is really these second phases. Didn't really change that much, but we had them. And if you look closely at them, they're not the same. They're a little different. And so what we tended to see, though, with low iron content is differences in the chemistries. So the low iron was rich in molybdenum and niobium, which sort of indicated the idea of law-based phase, but our high iron content became rich in titanium. And so there was a higher amount of titanium. So these were really titanium-rich precipitates. Now, how did this sort of dictate itself? It came out as significantly different grain structures. So low iron versus high iron. So we had this huge growth in our grain structures of our high iron. The other thing it did was we saw about a 25% difference in yield strength. Start putting that together is I've got materials that are nominally supposed to be the same specification-wise, have a 25% difference in yield strength. I've got some issues I need to work my way through here. Now, the precipitate morphologies ended up being different, but if we started looking at them, the low iron tended to be pinned on these grain boundaries. The high iron tended to produce a little more dislocation pinning. So let's get into sort of the future directions. I have a lot more here on this, but I do want to sort of cut it short. So, but what we see here is each of these precipitates are different. So the change in iron content actually impacted the precipitates that were present in the materials. So this leads us into sort of the future directions and sort of where I wanted to. You notice it's December 2015. I keep that up there mostly because there were a lot of things that came out of the road mapping exercise that we had, and it was funded by NIST through their original AmTech proposals. But most of what we talked about hasn't really been implemented, so I'm going to keep talking about and trying to convince people to implement some of the findings. What we were interested in was fundamental materials research. What are the enabling technologies on the materials side that would help produce more? And what we really found was this idea of integrating design. So you have to, in these roadmaps, you have to come up with some and so we identified some thrust areas, but if you really want to, you can contact me and I can send you an electronic copy of the roadmap. But that's sort of where I'm going to end. I'm going to end right on this nice slide here. And I noticed some stuff coming up in the chat. Hopefully it didn't distract me too much, but be happy to answer any questions. Thank you.
Thank you, Todd. That was a great talk. I must say I've learned a lot about additive today. I'm not in that field, but yeah, it's really been a great.
I would hope you would say I learned a lot about welding.
All right, so yeah, we have the first question here is from Jamal. And Jamal, if you're still there, please feel free to unmute yourself, show up and introduce yourself and ask that question if you would like, or I can.
Hi, Professor. This is Jamal, and it was a great talk, and I learned a lot actually. So I'm actually a PhD student doing in aerospace engineering. So I'm actually doing research in powder bed fusion process field. So yeah, my question was, I mean, during your nitrogen atomization process, was how much reactive was the nitrogen to the other alloying elements, and was there any intermetallic compounds as a byproduct of the process? So that's it.
So yeah, I'm sort of trying to run my way back through these. So um, so when you start thinking about it, you have to think about what the material is in your melt before you really start thinking about reactivity. Say, if I'm going to atomize titanium, I would be foolish to use nitrogen, wouldn't I?
Okay.
Right? Because what am I going to form? I'm going to form titanium nitride. So I'm going to make gold powder. Gold member, and Austin Powers might like the idea of this gold colored powder that I'm making, but it has literally no purpose. Now, when we're talking of using nitrogen, what we tend to find is that people will use it with materials and use nitrogen as the atomization gas in materials that it's compatible with. Stainless steels have a high solubility for nitrogen. So that's why the nitrogen levels went way up. It wasn't so much that we were forming a lot of nitrides, in which we did, but the iron itself has a high solubility for nitrogen. So it's great to use that. Nickel, on the other hand, tends to have what we might consider a lower solubility for nitrogen. So a lot of the 625 alloys that you might buy are going to be atomized with nitrogen. There's a little bit of an issue, though, there is nobody measured the nitrogen in the nickel-based alloys before because of that. There's no solubility for it. And I was guilty as anybody else of sort of saying that, is that there's no solubility for nickel, you probably can use nitrogen. We actually went back and measured the nitrogen contents. I didn't talk about it here, but they're higher than they should be. And we think they're impacting some of the follow-on precipitates that we're forming. So I hope I'm getting the answer to your question is it's alloy dependent.
Yeah, thank
you.
So
So you
much.
choose that atomization gas based on some of the thermochemical processes. We don't teach a lot of thermochemistry anymore, unfortunately. So there aren't a whole lot of steelmaking classes out there. And so, like I said, my advisor as a PhD started out as modeling steelmaking processes. So that was all I got. When I took thermodynamics as a graduate student, Carl Speer taught it. It was all on high temperature oxidation reactions. So it's good to revisit some of these things to sort of understand why people are doing what they're doing.
Okay, thank you so much for the answer.
So the next question is from Natalia. Natalia, if you can unmute yourself, introduce and ask a question if you want.
Sure. I was wondering, since you also measured the amount of other elements on your samples too, you had argon, nitrogen, and everything. And I saw that there was oxygen too. I see a lot of oxides formation after the 3D printing process, especially SLM, but I don't see much literature concerning the amount of oxygen on the inside the metals.
Yeah.
And how that would affect the pieces that are printed.
I see my student Andrew Imes on here. Andy, can you answer that question right off?
Yeah. So can you hear me?
Sure.
Yes.
Yeah. Okay. Great. So we're doing a lot of work with stainless steels here at Penn State, and we're studying kind of the role of oxygen on oxide formation. And one of the things that is I think pretty obvious if you start looking at chemistry of powder and comparing it to chemistry of wrought, is it's not unusual to see 4 to 5 times more oxygen in powder than wrought. And that's just the nature of powder in general, the propensity to sort of pick up oxygen, but those make them they make their way into the materials, and the higher the oxygen, you're going to start seeing the formation temperature of the oxides increase. And in addition to the fraction of the oxides will also increase as you increase oxygen content. And so it's, ultimately that's going to, both of those factors will result in more oxides in the microstructure. And they, as potential to seriously degrade mechanical properties. So yeah, it's a good, insightful question, and I think something that people don't pay enough attention to. So I'm glad you guys are also looking at that.
And I'll add to Andy's there, and what he's seeing is there's oxides all through these powders. And if you look a little more closely at the actual as deposited and heat treated, there's oxides there too. And so Andy's working in duplex stainless steels, which have a combination of ferrite and austenite. And the oxide inclusions are actually acting as heterogeneous nucleation sites for austenite. So there's a lot of really interesting things, and Andy's going to publish a paper here soon that sort of is going to track how these oxides change with post-processing. So the oxygen is a big deal. We've been ignoring it, like the smell from the rotting food in the refrigerator, but it's going to come out, and it's going to impact a lot of it. So.
All right. So the next question is from Eric. Eric, if you're still there, can you ask the question yourself?
Yes, sir. The only question I have is I've really enjoyed the lecture, and I really appreciate the detail in the slides, and they really speak to these conditions. Is it possible to get a copy of the slides?
Sure. Most of it's been published, so I think Ankit can give you my email address. And
Sure. Yeah, I'll be happy to do that.
Yep.
Thank you so much, sir.
Yep.
All right. The next question is from my colleague in chemical engineering, Professor MD. So Heather, can you unmute yourself and ask the question, please?
Yeah. So first of all, great talk. My background is actually in powder technology. So I do a lot of the techniques you mentioned, including DEM. So I was just curious to know a little bit more about what exact or what are your like ideal properties for your additive manufacturing application? So I know you mentioned spherical and you want it to flow well, but besides that, are there certain targets you're looking for your powders?
Oh, I think you lost me for a second, so I missed the question, so I kicked out. So if you could repeat that, that'd be great.
Yeah, so I do a lot of powder characterization. I'm familiar with like all of the techniques you mentioned, and including DEM. And I'm just curious on like what your target particle properties are specifically for your application. So you mentioned like spherical particles and you want them to flow well. But besides that, I was wondering if there were like certain targets you're aiming for your powders.
Not right now. I think part of what I see as the issue in the additive manufacturing field is that we don't know what we don't know. So, you know, back to the old Donald Rumsfeld ideas of known knowns and unknown unknowns. I think unfortunately for people in additive, there are a lot of unknown unknowns. And so we're really at this point just trying to figure out what we have. And so what the properties are, and trying to sort of figure out, you know, when you have a gas atomized, and trying to provide some of that baseline knowledge that would go into a specification. I'm sort of one of those, you know, sort of a bit of a dodge, but I'm trying to keep an open mind on what's needed, because it's not something that I think as a field we have a real good idea of what we want. So I'm not sure if that answered your question, but
yeah, it does. And just really quickly too, you mentioned that the powder, I believe you mentioned that the powder packing was a little bit more important than the flowability itself. Is that correct? Okay. So,
yeah, it's more in terms of sort of what's happening. I mean, there is some flowability aspects to spreading a powder with a blade, but not quite to the same extent of flowing a powder through nozzles.
Okay.
All right.
Very interesting. Thank you.
Thank you.
Heather. I have seen Bruno, you know, very impatiently trying to answer. He had a good question, I suppose, right? So yeah, Bruno, there is, he's a colleague of mine in Poly School, and yeah, Bruno, go ahead.
Thank you, Kumar. Thank you, Krishna, for organizing this, and thank you for our speaker. I really enjoyed the talk, and we've been working a lot with powders in our lab, and So it's really exciting to see this, and most of my students, if not all of them, are here today. So one of my questions is, what are some of the strategies, whether it's heat treatment or even maybe other strategies to introduce, to play with the powders and the mixtures of powders to try to get rid of some of these uncertainties? A lot of the things you talked today, I felt they are uncertainties that are, that need to be considered. But how do we make it simpler? What are some of the strategies? Either, let's say, is it possible to introduce certain nucleants into the powder bed, into the mixture, to kind of standardize how we get the final structure, or introduce a little bit more forgiveness in this process? Even like, for example, the nitrogen content, right? This differences in content in the absolute scale is very small, but it showed that it's such a dramatic effect. And so some of these things are really interesting, but what are some reasonable strategies that we can negate, or we can reduce the uncertainty levels?
Yeah, I think, at this point, I don't think things are going to open up to sort of make things easier. I like to sort of think about welding. We talked about, additive manufacturing being very similar to welding, and a lot of the same basic features that we see in welding are observable in additive-based processes. The difference is really in sort of the fundamental, the philosophy of it. So how did welding ever get to be so accepted? Why is it so widely accepted? And what it is there's a set of very strong specifications and codes out there of how you do things. And welders achieve this by putting a lot of constraints and boundary conditions on things. So if you want to weld structural steel welding code, AWS D.1 document, it's like that thick. It tells you what your joint's supposed to look like. It tells you what the essential variables are that you need to control. It tells you what filler metals you need to use with certain material combination. It tells you everything that you need to do in there. And they constrained everything so that they got repeatable results. What did we do in additive manufacturing? Said constraints, threw all the constraints out, threw all the boundary conditions out, and now we have an unbounded problem, right? Because we took all the geometry, we took all the material, we're using powders that have all of these different alloying elements that we didn't have to worry about before. So I think, as far as a certainty thing is, now you have to start pulling back the constraints, sort of have to start pulling the strings and getting things back into a controllable type environment before you really move forward. So I think what you're going to see is really the standards organizations that really give it thought are going to be saying, okay, you're going to use a pH grade stainless steel, you're going to use, this is what you're going to do. And these are the only conditions you're going to do it. We're going to have really tight constraints on powders, especially for critical applications. Because from what I can see here, the problem really in additive becomes is, it's not so much that the properties are better or worse, typically because of fine grain structure and some other things are going to be better. Our problem is the statistical probability of that 1 in a million failure is now about 1 in 10,000. And for critical applications, whether it's in aerospace, whether it's rotating engine components, is just completely unacceptable. And so, things are going to get squeezed and then they're going to come back out. I think that's the only way I see us really able to do that. I hear a lot of people talking about nuclear, and my student Andy, who answered the question before, came out of the nuclear industry. And, we can just chuckle sometimes of people thinking you're going to put components in a reactor. Department of Energy, or the Nuclear Regulatory Commission, just recently approved a new material for use in nuclear power plants. It was alloy 617. It was developed 45 years ago, and it was just approved. So I might have gone around a little bit on your question, but did I sort of get to what you were after? Or were you
Yeah, I
looking
liked
for
it.
something
I liked it a lot. It's very nice coming from a metallurgist expert and getting their perspective on the subject. Very helpful. Thank you very
Yeah, I
much.
mean, 'cause look at what we do with Ti 6.4. I mean, that alloy was developed for the SR71. And we use it as like, does anybody, nobody knows another titanium alloy, do they? So.
Very nice.
Are there any more questions from the audience? Okay. All right, so let me just ask you one final question in that case. So I got very excited when you actually brought in the computational thermodynamics, because, you know, I am a thermodynamics person.
Yep.
So, well, I think many years back, all of these non-equilibrium processing started with the time of Wilfried Kurz in EPFL, Lausanne, where he came up with these so-called solidification microstructure selection maps, where you didn't just have the equilibrium phase diagrams in, but you actually had a metastable phase diagram. Now, with the incurrence of additive manufacturing, most of these processes are non-equilibrium. So how reliable do you think it is to rely on the equilibrium phase diagrams, which only gives us idea about mostly about, you know, the equilibrium part of it, and not really what's going on in the non-equilibrium state?
Yeah, they don't tell us much of anything, really. It gives us sort of that idea. They're really great once we start post-processing and heat treating to a point. They're giving us a lot of insight into some of the things we're seeing. Now, as a predictive tool, you're right. They're not going to be, you know, thermal calc gives us a lot of great information, but we need to come to that realization that we're talking about equilibrium conditions. One thing that we have seen that it is seemingly giving us a little bit more of a predictive capability is going back into fundamental solidification theory and really using sort of the Scheil-Gulliver type simulations across, you know, sort of a liquid solid, you know, two-phase region, looking at, you know, it's diffusion in the liquid, no back diffusion into the solid. At the rates that we're seeing in most of these, we're seeing that the Scheil simulations are doing a decent enough job. It's not perfect, but it's letting us sort of see this partitioning. And this is where you need to get crafty in how you apply computational thermodynamics, because the minute you have that Scheil like segregation and you're getting these alloying elements in places where they didn't belong, you're actually making a multi-alloy part. So in, say, the Inconel 625 or 718 is a great one right now. When you start segregating out the niobium and you have enough carbon in there, you're going to form niobium carbides. You go back to your thermal calc and you start thinking about that, you see it never goes away. Yeah. Stuff's coming out of the solid. Andy, my student Andy's doing stuff showing that as you increase the oxygen content, all of a sudden spinel is showing up, rhodonite, all of these different things. So they're really useful tools for providing that. I don't think we're at a point where it's predictive at all. You sort of have to, one of those things where you have to understand the process a little bit, you have to know what you're doing to use them. This is not just somebody coming off the street or, you know, an undergraduate going there and just using it like they would. It's not like Microsoft Word or Excel or something.
Absolutely.
There's a real danger when people start playing around with it, you know, and sort of, I don't know how many mechanical engineers are here, but, you know, sort of keep your, you really need some adult supervision with some of these tools before you start really applying them in anything too critical.
Great. Yeah. So yeah, so that's great advice. And I think because we don't have any more questions, we can wrap it up here now. And I thank you all again for attending. And Todd, it was again a great talk, great honor to have you here. Keep on.
Thank you for having me. Too bad I couldn't come out to Arizona for this.
We would have loved to have you here. Yeah. In fact, we have Sudarshanam Babu a few years back here. You know.
Oh yes.
Yeah. So additive is something we want to really.
Absolutely. I worked on the synchrotron beam lines with Suresh 20 years ago.
Oh,
so,
nice.
Yeah, so I've known Suresh for about 25 years. So
that's great. All right. Thank you, guys. And
Ankit, just wanted to add a couple of things. One's, Todd, I think there's a polo that we designed that'll be heading your way soon. The idea was all our speakers would be wearing those polos when they give this talk, but
Oh, well, I thought I went the step above with the tie and the jacket.
this is great.
Great job.
But yeah, it'll be coming your way as soon as we figure out the logistics with all the COVID things going on. And for what it's worth, there are going to be a few metallurgy / additive talks in the seminar series. I think the next 2 talks, one's from HRL on the aluminum alloys, and that's going to be followed by a talk from SLM. Don Godfrey, who was at Honeywell, and he just moved.
Okay. Yep.
And then John Carpenter from Los Alamos is going to be next semester, right, Ankit? If I'm not mistaken.
Okay.
So
yeah, I know John well is
yes. So there is a revival here to get metallurgy back on track, and with the additive manufacturing buzzword attached. That's the
It definitely is, and I think, you know, with the current COVID situation, hopefully people are seeing the value of bringing some of these technologies back on shore.
Yes. Cool. Thanks a lot, Todd. Thanks, Ankit.
All right. Thank you all.
Bye, Christina. Bye, Bruno.
Bye-bye.
All right. Well, I'll hang up.
Bye,
Thanks,
Todd.
guys.
Bye.
Bye.